report on this computer. All right. So in module 6, as we look at session number 1 here, because we're kind of officially, last time we were together, we were finishing up and working on the tail end of learning plan, or I'm sorry, module number 5. Now we're on module number 6. And here we're going to be kind of back in our book, the tech drawing book, and we're going to be looking specifically at chapters 12 and 13. Okay. Chapters 12 and 13. I know it's kind of a lecture day, but that's okay. This is kind of information that we need. We can't be AutoCAD fun stuff all the time. Okay. So this is what we're going to be doing today. So for those who are in class, you'll be kind of looking at the screen here. For those who are off, then you can either reference this PDF or follow along as well. So as we look at chapter 12, this is chapter 12 in our book. We're really going to be looking overall in tolerancing. I'm not going to read this list to you, but we're going to be kind of hitting all of these items as we go along. So first of all, understanding tolerancing. Now we've talked about this a bit. All right. We've talked about this a bit, but basically what tolerancing is it's setting up for us the target that manufacturing has to hit on a feature in order for when it comes together and it's in its physical form and it's going to be part of an assembly, that it's going to fit together and function properly. Okay. You as the designer, that's your job. Okay. That's really what we're training you to do. And that's the practice we're going to be looking at. We've talked about tolerances. Now tell me what you know about tolerances to this point, even those who are online. I'm going to watch the chat, or you can chime in audibly. I'm going to make sure that my speaker is on. Okay. So that I can hear anybody, but tell me what you know about tolerances to this point. I mean, we're dedicating a whole chapter to it. There must be something. Yeah.
Tolerance is how far off of the specific direct dimension that you're allowed to go.
Yeah. So tolerance, as Joshua said, is going to be how far away from the amount that we can be away from a dimension, or maybe a nominal value, we might call it, right? Okay. Anything else we know about tolerancing?
Specified on the title block, which is otherwise specified.
That's right. So in the title block, we have standard tolerances, right? So we specify them, for instance, for an inch increments, the decimals. If we have 2 decimal places, we have plus or minus 10 thousandths, right? Plus or minus 0.01. Or if we have a 3-place decimal, it's plus or minus 5 thousandths, right? And what that means is if in the drawing itself, and there are a number of dimensions that we've put on drawings already that have no tolerance specifically in back of it, but every dimension on a drawing has a tolerance. And if it's not there, like Josh said, then it defaults to the title block. So every dimension on a drawing has a tolerance. Whether you intend it or not, it does. It does. Okay. So a tolerance is going to be that amount that is allowed to specify. So we have to think about, we can't just willy-nilly just set up for 2 decimal places and like, here are the dimensions. You have to look to that title block and keep in mind what that plus and minus is, because now that's the target that you've set for that dimension intentionally. All right. You have to think about every dimension that's on there and its function, its purpose, how accurate it has to be, and how it's going to be manufactured. Okay. So as we look here, understanding tolerancing, it's a total amount of a specific dimension is permitted to vary. Okay. So again, I like to say it's the target. How wide is the target, or how narrow is the target? What do I have to hit? Okay. To effectively provide tolerances on your drawings, you must understand the fit required between mating parts. Okay. So in the end, do I need this to be a clearance fit, meaning that they're going to go together really easily? Or do I need this to be a press fit? Do I need to kind of push that together and then they're going to be, nice and snug relative to one another so they don't move around in their final form? I don't know. It depends on the function of that part. We say that so often. Okay. You need to have a clear picture of how inspection and measurements are going to be performed on that. We make a part, we make a feature on our drawing, and we think it's going to function. It has to, number 1, be manufacturable. And number 2, then we have to be able to check it. Okay, so we have to think about inspection. be able to apply those tolerance symbols to a drawing or a model. So as the designer, you have to put them on per the standards, okay? And then apply functional tolerancing to individual features or a part, okay? So again, thinking about every one of those dimensions you put on an individual part and how it's going to affect its function in the end, okay? So tolerancing is really important. Now, quality control, before paying for parts, most companies have a process to quality certify their parts against the drawing or the model. Meaning, let's say we make a bin of parts and we have to check to see if they're good, if they can continue on in the process, maybe go on to be assembled into whatever the final form is going to be. Well, those drawings are going to be checked, meaning if we have a dimension or each one of the dimensions on the part have to be inspected by somebody in what normally is called the quality department. And they are going to say, are those parts okay or not? Now, depending on how many parts are created, you may or may not check each and every one of the pieces, okay? So you may have something in place where you kind of pull out a number of pieces every hour, and that's kind of checking your process, okay? And so they're going to then target the important dimensions that are going to be critical to how that's going to function. Okay, so they're going to check that. So as we look over here, this is kind of a nice little illustration. You'll notice that we have the drawing. We have 1.625 plus or minus 2,000. So what that means to us is our nominal or our middle dimension is 1.625. This is allowed to vary plus 2,000. So we're going to add 2,000. So my high number here would be what? 1.627, right? So I can go up to 1.627 and I can go down to 1.623. Okay, that's the target that I'm trying to hit. And any number in between there is good. Okay, it also means that any number along there has to be the number along the entire length of this feature. So if this is 3 inches long, no matter where I measure along that 3-inch length, it has to be between those two numbers. Okay, so you'll notice that what's created here, and that's why I like this illustration, we see like this cylinder, okay, that has the wall thickness, if you would, equal to the tolerance zone that we're looking at here. So the inner diameter is 1.623 and the outer diameter is 1.627. Those create what we call the envelope for which all of the points along that length have to be within. If at any point I measure with a micrometers, have you guys had micrometers in your manufacturing processes yet? Yeah. Okay. So you know what I'm talking about. I'm measuring with my micrometers or my calipers along that length. And if I measure 1.622, am I okay? No. If I measure 1.629, am I okay? No. Which one can I maybe save? Why? The 629, that's right. Maybe the 629 I could save. Why? Exactly. So when I'm making this part, more than likely, I'm going to be turning it on a lathe, right? You guys know what that looks like. You're going to be turning it on a lathe. That means that I can still maybe put that back in the lathe if there's too much material, if it's on the high side, we say, and I can take a little bit of material away and bring it down into tolerance. But unfortunately, if it's on the small side, that material's gone already, right? And I can't put it back. So sometimes we can salvage parts, all right? But the drawing right here, this is what they're checking every part to. So when you put a dimension on, know that it makes it, I mean, it's not just about putting it together, but now they're going to be checked to that. And now if there's problems, guess where they're coming back to? Your drawing. You're going to get involved, okay? So you have to be able to say, I use that tolerance because, right? So there has to be thought, there has to be intention with each one of those dimensions. I can't emphasize that enough. It might seem a little like, really? I'm like, yeah, really. Remember what did I say about the documents that you're creating? They're what? They're put in a drawer and they're never looked at again. What are they? In a company, their relative importance is what? When you make a drawing, is it like high importance? Is it like a big deal? Or is it like, It's a totally big deal. It's a totally big deal because why? Tell me. This is really important. This you have to keep in your mind all the time. The job that we're training you for is very, very important. But why is that drawing so important to a company? What does it drive? No, yeah, everything. So ish. But what is one of the biggest when a company is in business, what are they trying to do? Are they there just to have fun? They're there to make money, right? And if they don't make money, what happens? Well, they can't pay their employees, right? And we're all, I'm not going to lie. I come to a job, we all go to a job, and it's exchange of time for money. That's what it is, right? And if a company cannot make their payroll because they didn't make enough money, then all of a sudden you're out of a job, or they can't employ other people as well, right? Now, at the core of that making money are the parts that they're providing. And see where I'm going with this? You have a direct effect on the cost of those parts. The lower the cost can be of that part because of the design that you create and the dimensions you put on, literally the dimensions and the tolerances that you specify are going to drive the cost of that part, how it's going to be made. Then it's that difference between what they're selling that for, it's the profit that they can make so that they can continue to be in business and pay your paycheck every couple of weeks. It directly affects you and everybody else that works at that company. So I can't put enough importance on this. Okay. So when you're doing these drawings, when you're putting dimensions on, especially the dimensions and the tolerances, they have a huge effect. They have a huge effect on the livelihood of that company. Now you might think, really? Yeah, really. So I'm excited for you guys. You get to do that for a living. So that's really cool. All right, so let's look at some definitions for size designation. So we throw these around a lot, okay? We've heard feature of size, actual, well, maybe not actual local feature, but you've heard me say nominal size quite a bit, okay? And then we also are going to have allowance here. So nominal size, let's identify that first and foremost. Nominal size is when we have, it's kind of like I'm not going to say it's always the middle, but it's usually the middle dimension. So for instance, if we're in the English system, nominal sizes are going to be to those nice fractional increment numbers. So for instance, 16ths, 32nds of an inch. So here we have 1.25. That's a 1 1/4 inch diameter, right? That's a nice number. That's called a nominal number. That's the number also that a drill would be made to, okay? And why would that be interesting to me? If I make it to a drill size in to manufacture that feature, now I have one tool that I have to pick up to make that feature and I'm done, right? The less I have to touch that feature, the less time I have to spend on it, the lower the cost, okay? So that's why when we put numbers on, we want to make them nominal values that are going to relate to tools that can be used. So when we think of holes, okay, what are the standard drill sizes? Okay, have you guys drilled holes yet in manufacturing processes, put holes in with like a drill press? Okay, well, drills come in standard sizes, and in the inch increments, they're going to be usually to like the 32nd of an inch or so. We're going to be looking a little bit later. I do have a chart for you guys, a drill chart that is standard so that you can see, what is standard. So when you're putting sizes of holes on, you want to be to a nominal size. Same thing for metric, and those are usually to about the millimeter increment, okay? Because they have drill sizes that correspond to those, okay? So nominal size is going to be that nice number, okay? That nice number that is going to relate to something, especially in the system of measurement that you're looking at. Now, allowance. Allowance is going to be the intentional degree of either clearance between the internal and the external part. So the internal part would be our hole. Our external part would be our pin or our shaft. If we want that pin or shaft to fit in that hole without having any problem getting it together, meaning we want to provide clearance between the two at all times, then we're going to intentionally create an allowance so that there is no interference of any size, okay? And you as the designer get the control over that. You get to tolerance the pin, and tolerance the hole so that they fit together with a clearance fit, okay? But you can also have an allowance that is what we call a negative allowance or an interference. And what all that means is, okay, now we're going to intentionally have the material wanting to occupy the same space, if you would. And sometimes we want that. Sometimes we want what we call a light press fit or even a heavy press fit, okay? And that's so that when we press them together, those parts don't move relative to one another anymore. They're going to be right there. So when we put bearings in place, we press them in so that that outer race is not going to move around. Okay. We don't weld them in. We don't screw them in. We press them in. Okay. And it's actually a pretty accurate, probably 4 or 5 decimal place fit. Okay. And then there's other different types of elements that we would press that might even require, you know, hammering it or convincing it to get into place as well, or pressing it in. Okay. Variations along the form. So as we create that envelope that we saw earlier, so for instance, so we're going to go back just a little bit here, this envelope created by the maximum and the minimum size, all of the points along that pin in this case have to fall within that envelope. Okay. And so they can take a lot of different forms. They can take a lot of different forms, meaning they can look kind of, you know, like hourglass. They can look bowed along the length. They can be tapered. They can also kind of take this like barrel effect as well. Okay. But as long as they don't violate that min and that max value, they can look like this. Now, when we look at them with, you know, just kind of on the table, a lot of times this is within 10, 15 thousandths. And we're maybe going to look at it and be like, oh, that looks good. Okay. It's not until you really start measuring it or rolling it or maybe scanning it that we're going to really notice the big differences. Okay. And that's what the quality department does for us. They're the ones who specialize in checking to see if things like this, you know, are occurring. Okay. And if it's a problem. So material envelope, and we've kind of looked at this really in very simplest forms. It's going to be looking at the shape of that part along its entire length as it fits within the confines of that minimum and maximum value that create the min and the maximum extents of that envelope. If any part extends outside of it, whether it's towards the inside or physically on the outside, then it no longer meets the specification and they would be rejected parts, okay? Because they would be assumed not to be able to fit together, okay? Now, right angles are implied when we create them on drawings, meaning we don't dimension the 90-degree angles. You've probably noticed that already. We only dimension angles that are anything other than 90 degrees from one another. So, but when we have the 90-degree angles, the tolerances in the title block still apply. In the WCTC title block, we have the standard title block tolerance for angles to be what? Tell me what they are. You should know these. Nope. Not plus or minus 5 degrees, plus or minus 0.5, a half a degree. Okay. That's a very common one. In this one, they have it plus or minus a degree. Okay. So you're always going to want to become familiar with your company's standard, or if you're working with other companies, sometimes you might be on the side of you're a contract manufacturer and you're looking at other people's prints all the time. You have to look at that title block to know exactly what that is and what that spec is so that you're inspecting and making those parts to the appropriate tolerance. All right. So 90 degrees are always going to be implied. Fits between mating parts. As we said earlier, we can have clearance fits where there is actually air or intentional, you know, clearance and they go together easily, or we could have something that's a little less clearance. Now, in this case, we have a smaller tolerance. Okay. So, so you'll notice that we have an allowance here that is going to still fit, but you can see that the relative looseness between the parts is not as much. So here we have a diameter of 1.248 on our pin, and then the diameter of the hole is 1.250. My assumption here, and as we look at this, is those are the actual sizes that they're made to. So in the top case, you'll notice that we have more clearance. So they kind of, you know, exaggerate the amount of space between the two. Okay. And then down here, it's not as much. All right. So you as the designer get to control that, okay? So when we tolerance holes and pins to fit together, you'll notice that we're going to add these limit dimensions. And as we look here, the critical dimensions that we're going to compare are going to be smallest hole, largest pin. Why would that be the critical side that I would look at? Smallest hole, largest pin. Why would that be like the biggest deal? Tyler?
If you're gonna have an interference.
Yes, I like to call that my worst case scenario, okay? Because the hole is as small as it's going to get, right? That's as bad as it's going to be for the largest pin to actually fit into. So you always want to compare those two and you want to see where are you at. So when we look here on our hole size, we're at 1.25. And when we look at the largest pin, we're at 1.248. Am I going to have a clearance or an interference? I'm going to have a clearance, right? I'm going to have a clearance all day long because my smallest hole is larger than my largest pin. Okay. Let's look down here. What about these? Now, these are made to 4-place decimals. Okay. Not a big deal, right? That's okay. It's just that it's a more accurate level of tolerance and they're specified here. Now, let's say I'm just going to put this out here as a hypothetical. Let's say I would put 1.25 as the diameter on that with 2 extra zeros. So it will be 1.2500 on our WCTC border without a tolerance in back of it. Is that okay? Go like this. No. And it's not okay because why? It's a 4-place decimal. Why is a 4-place decimal just by itself without having a limit or an extra tolerance not okay on our WCTC border?
The extra decimal places that warrant the different.
Yes. So the only thing that our title block covers are 2-place and 3-place decimals, right? That they get the default tolerance. If you put a 4 or a 5 or anything else on there, it's not covered. So somebody's gonna be like, okay, what do you want? What do you want? What's the tolerance on this? And you'd be like, well, oh, okay. I caught that on some people's drawings. When you're going in, if you don't change the number of decimals to like a 2 or a 3-place decimal, and you put 4 decimal places on everything, your title block isn't covering anything. There's no tolerances there. That's a problem. Okay, so watch that. All right. In this case, they do have the limits dimensions. The limit dimensions are going to be a dimension that's going to show me the high value and the low value. Limit dimensions are nice. And especially when we get into critical things. I worked for a company where if we had anything that was other than the title block tolerance, we had to put the limit dimensions on it. This eliminated anybody making any mental math errors, okay? Because they can happen. That's going to be an induction of a human error. So whenever possible, if you deviate from the title block, it's always a good idea. Limits are just nice. Nobody has to do any mental math in their head. So anyway, these are limit dimensions on both, which is good. So now I'm going to take the smallest hole, 1.25, and then I'm going to compare it to the largest shaft or the pin. So 1.251, What type of a fit do I have here? I have an interference fit, right? Because now my smallest hole is smaller than my largest pin, right? So when I put them together, I'm going to have, it looks here like I'm going to have, you know, worst case scenario, 1.9, I'm sorry, 0.0019, not much. 19, what we call tenths of 1,000. Okay. Whenever you're in manufacturing, you probably have gotten this in your manufacturing processes class. We talk in thousandths of an inch, right? So we say 5 thousandths, 10 thousandths. In this case, it would be 19 tenths of 1,000th because you're out to that extra decimal place. Okay. So you'll hear that a lot. So yeah, we've got an interference here. So we may have to either pound or press that together. Okay. All right. Now, I'm going to zoom out here just a little bit. Okay. Limit dimensions are a method of directly specifying the tolerance by providing the dimensions for the upper and the lower limits, as we said earlier. So when we are looking at identifying what the limits are, we are identifying what is that up or that top value and what is that lower value. Okay. And again, it's really nice because you don't end up having to do any of the math, if you would, on the spot. Now, selective assembly is when all the parts are inspected and classified into several different grades. So sometimes this might be where you have certain parts that fit together and certain parts that maybe don't. So you might line up the hole to the shaft. But I will tell you, this is not something that you want to count on. A lot of times companies just want to have their bin of their parts and their other bin of their parts. And now we're just going to start putting them together. So you can't plan for some of them not fitting and some of them fitting. All right. You have to be able to dimension so that everything is going to fit together with the appropriate fit. Now, there is a whole system, and the whole system is how we tolerance our parts. So for instance, when we look at the hole and the shaft that are going to go together, and this has to do with manufacturing process. So the basic size or the nominal size will always go in the hole system on the hole. So you'll notice here when we put these two parts together, I have 0.5 as my minimum size hole, and then it's going to go up to 0.502. And then over on the right-hand side, the pin that's going to fit in here, you'll notice that its maximum size is 0.498. Notice that the nominal size of a 1/2 inch is on the hole because I have a drill that's going to be a 1/2 inch, right? That I can pull out and I can make that hole with, right? Over on the right-hand side, when I make this pin on a lathe, how do I make that? That tool goes in and it touches the surface. And now I can make that smaller a lot easier than I can make a hole like a weird size. Okay. So my nominal size is going to be 95% of the time, 98% of the time on the hole. That's called the hole system. Okay. And then any variation is going to go on the shaft because I can turn this down. When I look at the next slide here, this is where we call this the shaft system. This is when the nominal size is on the shaft. Okay. And you'll notice here then on the hole side, we don't have the 1/2 inch. The 1/2 inch is actually on the pin. Now, this might mean that I'm getting in specialized material that is ground and hardened, and I don't want to, turn this down anymore. And it's coming in at a 1/2 inch. Okay. That's its nominal size. So now I got to make the hole to accommodate this. It doesn't happen all that often. The more popular one is going to be the hole, the basic hole system where the nominal size is on the hole to accommodate a drill size. In this case, my drill, I could drill it out to a 1/2 inch, but it's going to take another operation to probably ream it out to get it to the size that's here. Now we might not think, oh, it's no big deal. We can ream it out. That's not a huge deal. Well, in the cost of the part, the overall cost of the part, it is a big deal because now it's adding an operation. And that's time is money. Okay. So the cost of the part went up. And that's where you as a designer get to decide, what do I want to do here? Is it more important to save the money on the hole size, so I just have to drill it? Or do I need that ground and polished, 2 size shaft? I don't know. You got to look at the application. Okay. So just know that every dimension, when it comes down to it, the tolerances that you specify are they're going to dictate the manufacturing process, which then is going to drive the cost of that part. Okay. That's why you guys take manufacturing processes. All right. We're not expecting you to be machinists in the end, but we want you to think manufacturing process. How is this going to be made? How does that equate to cost? You're going to be and you may have done this already, but in manufacturing processes, you get to see how different or how hard is it to get to the target of a 2-place decimal as opposed to a 3-place decimal, as opposed to a 4-place decimal. So then you start to see how the number of decimal places is going to affect how long it's going to take to make that feature. Okay. So that's the difference between the basic hole system based on a drill size or the basic shaft system based on the shaft size. Okay. All right, general notes. And we've encountered this in the dimension that we've done. So all tolerances are going to be blah, 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 unless otherwise specified. Okay. So these are going to be kind of those standard title block notes. And we've talked about this before. Limit tolerancing having that max and that min value right there, right by the dimension. It is the ideal way, especially when we have critical features that we need to control the tolerance on, okay? Putting the limits out there is always a good option. Single limit dimensioning. Yeah, I think I have to zoom in here. This got really, whoopsie, other way. This got really small. Single limit. So the note min or max is placed after the number to indicate the minimum or the maximum dimension desired when the other elements of the design are specified. Now, they have this so small on here. It might be better to see it. I don't even see a min or a max. I don't know what they're referencing in this case. Let me just see if I can find it in the book. Maybe they have the wrong thing called out here. Single min max. Yeah, I'm not exactly sure what they're referencing here in terms of min and max, because on that drawing, as I'm even looking inside, I'm not seeing any reference to a min or max on any of the dimensions, but that's okay. That's all right. Plus and minus tolerances. These are very typical. Now, when we look at plus and minus tolerances, they can also be unilateral or bilateral. Okay, let's look at examples of each. So in back of the of the nominal value, if you're going to see a plus number and a minus number, and this is going to be different than what's in the title block. So we only add these when they are something other than the standard title block tolerances. So here you're going to see we have 1.878 plus 0 minus 2. Okay, so what I want you to do for each of these 4 dimensions on a piece of paper on the side, write out the max value and the min value, and then we'll compare. So I want you to look at these numbers and see if you can find the max and the min numbers for each one of these tolerances. So for the first one that we have here, the 1.878 plus 0 minus 2, this is a unilateral dimension, meaning all of the tolerance is in one direction, and all of that direction is minus 2. Okay, it's a plus 0 minus 2. So if we look at the limits here, the top limit 1.878 is going to be adding 0.000, right, or 0 thousandths. And then the bottom is going to be subtracting 2 thousandths. Here's that thousandth space, right? So this is going to be 2,000. So this is going to be 1.876. These are the limits. This is the high limit and the low limit, creating the envelope for which all of the dimensions have to be within along the entire length of that feature. Okay. Let's do the next one. The next one, this is not a unilateral. This is a bilateral, meaning I have some tolerance on the top, some tolerance on the bottom. Now, this is an uneven bilateral distribution because I don't have the same number top and bottom. So in our title block, that's a bilateral equal distribution because it's plus or minus 5 thousandths. Okay. But here I have plus 2 minus 1. So that means that I have a bilateral, but it's not even. So here my high limit is going to be 1.878. And it's going to be the low limit is going to be 1.875. Okay, so we take this number and we simply add and subtract. Okay, Any questions on that? Determining limits off of a dimension. Okay. Then down here, we've got another unilateral, but this is a metric value. So this would be 47.70. And then below is going to be 47 point. Now this is going to be 0.5, subtracting 0.5. So this would be 6.5, right? So high limit max, low limit min. And then down below further, I would do that 47 point. Now I'm going to add 0.05. So that's going to be 7.0 on top. And then 47 point, and I'm going to subtract 0.03, which is going to be 62. High limit, low limit. Any questions about that? So we can see these are all valid ways that we can show tolerances. We can default to the title block, and then we have to figure it out, right? With a min and a max, we can show the limits, or we could show the actual tolerance in back of it. Okay, actual tolerances in back. Angular dimensions, okay? So angular dimensions are usually going to be bilateral, okay? Or they can be given in the degrees, minutes, and seconds. We don't see that very often at all, unless you're in an industry where maybe you have a timing type of an indicator, but most often we're going to be to the closest decimal degree or half a degree, okay? So, so you can do it in degrees, minutes, and seconds. Now, tolerance stacking. Whenever we dimension something, we know that we're going to be identifying, especially locations and sizes of features. Now, as we look at this part down here, you'll notice that we have two different versions of how to dimension. The one on the left is called baseline, and the one on the right is called chained or continued dimensioning, okay? Over on the left-hand side, to get to each one of the steps here, you're going to notice that we're measuring each time from what we would call a datum, okay? Because that's like the start point for all three of those dimensions. So it means that the step length here is going to be 1.000 to 0.995. And then the next one, measuring again from that original base to the second one, is going to be this dimension, and so on. So if I would measure the tolerance for which that step, each one of these steps has to be within, you'll notice that they have to be within 5 thousandths, each one, right? From that original location or that baseline. Now, over here on the right, notice that we have the same tolerance between each one here. But now when I get to the very end, this last one depends on the higher or the lower of the first one and the higher or the lower of the second one, okay? This is called an accumulation of tolerances, meaning if I'm on the high side for the first two, I'm going to be at 2 inches. And then on the high side here for the third one, I'm going to be at 3 inches. But then if I'm on the low side, low side, low side, now all of a sudden I'm minus 5 thousandths, minus 5 thousandths, minus 5 thousandths. And this number is going to be 15,000. So it would be 2.975, right? No, 2.985, 2.985, where over here, this was 2.995. And that's an accumulation of those tolerances that are stacked up simply on the way it's dimensioned. Notice that if I dimension baseline over here, all of a sudden I have my 5 thousandths. Over here at the end, it's going to be a difference of 15 thousandths. Okay. Guess who gets to control that? You do. The designer does. And guess what dictates that? This decision. Is either one of these a bad decision? No. What does either one of these decisions depend on? Number one. Starts with an F. Function. It starts with the function. You as a designer know how that part's going to be used in the end. So you are going to decide, okay, how critical do I have to have that? So the function is going to dictate number one. What is the second consideration that you need to think about? Cost, which is dictated by what? The MP. The manufacturing process, right? Because it has to be made. I can make a perfect design and it's all going to fit together perfectly, but if it can't be made, well, then it's not really a good design, right? No longer a good design. So you have to think about that. You also have to, depending on the shop that you're in, if you're going to be making these parts in-house, you're going to have to take into consideration the capabilities of the machinery that you have available to you. Okay. If you can make it to 5 decimal places, but you have to ship it to China to do it, or to Oklahoma, well, now you haven't saved any money, right? You have to maybe find ways that you can get around it. So you also have to think about the capabilities of what you have at your access. Okay. Probably don't have to ship something for 5 decimal places to Oklahoma, but there might be someplace in Milwaukee that you can do it, but it might not be in-house. Okay. And that's a consideration because that's added cost again. There are standard sheets or standard limits that we're going to be working with. Now, I'm not going to dwell on this too much in this particular chapter because we're going to have lots of opportunities to add these and look at these charts in other instances as we go along in mechanical design. But know that we do have a standard, what we call clearance fit charts. Okay. And what they do is they take your nominal size, you find your range of your nominal size. So for instance, if it's 1 inch, I would be on this row. And then I'm going to go across and I'm going to then specify what is my hole tolerance and what is my shaft tolerance in order to get what we call a range of a fit. Okay. So an RC fit is going to be kind of a loose fit. And then these numbers over here are in thousandths of an inch. So we'll get practice doing that at a later date, but know that there's standard charts here. Now, tolerances and manufacturing processes. So we've kind of been talking about this relationship all the time, but this is a nice chart that starts to show you different types of processes and what they're capable most often of doing. Okay. So at the bottom of the chart here, you're going to notice we have drilling. And here is the range where you see this band. And if we go directly above, these are the tolerances that we can expect. Okay. Meaning for the size that we're looking at, so smaller sizes, we can expect closer tolerances, but as we get larger, kind of that, kind of the scaling makes it harder to hold those tolerances or even lengths. The tolerances go up a bit. Okay. So if I'm trying to drill a hole, for instance, that's 5 inches in diameter, the tolerances aren't going to be expected to be as close as if I'm making one that's 1/4 of an inch, which really kind of makes sense. Okay. So that's going to be the range, if you would, that you can get for drilling, but you would want to know the capabilities of the processes you're dealing with. Milling gets a little bit more accurate. Notice that we go over a tad. Turning, boring, slotting, planing, and shaping, a little bit more accurate again. Reaming, broaching. Then we get into grinding, diamond turning, and boring. And then lastly, lapping and honing. Tell me what you think happens to the cost when I move from the right to the left. The cost goes up, right? Every level that I go up here, all of a sudden I am going to increase the cost and the, if you would, like the, I want to say how, like, how there's specialists in different industries, it becomes more specialized as you go up too. So the equipment becomes more expensive, the people running it become more expensive because they're more specialized in that area. So, so yes, the cost definitely goes up. The 3 big ones that we deal with are going to be drilling, milling, and turning. Those are like standard machine shop. Those are your lathes, your mills, and your drill presses. Okay. And then cutoff saws and stuff like that. Reaming is actually not a bad add-on either. That's usually a standard machine shop capability. But once you start getting up here further, broaching machine is specialized. Okay. You may have to buy one potentially, but then when you get into grinding and lapping and honing, grinding machines are going to be in your tool room. Okay. And the tool room, I call it the magical place because everything that comes out of the tool room is really expensive. They're usually making your gauges and things like that. And it is a magical place, but it gets really expensive. So these 3 right here are going to be like where you want to sit, if you would. And that means that you're dealing with this side of the chart. Okay. So manufacturing processes will help you to just kind of, relate to those numbers as well. Okay. Now, the metric system and tolerances and fits, they have their own ways of tolerances and fits. And again, this kind of speaks to those charts that we talked about earlier for English. We will be hitting those along the way, and we're going to be doing that a little bit later in this class through the AutoCAD drawings and designs that you're going to be doing yet in the last couple weeks here. The second to last slide here, geometric dimensioning and tolerancing. Geometric dimensioning and tolerancing is a set of standardized symbols that are going to speak to form and function of features. Okay, we have a class dedicated to GD&T. Did you know that? So if you look on your list in your program, you're going to see a GD&T class. Okay, everybody takes it, and it's going to be offered. I believe it's going to be spring 2 term. And so it's a really good class. So we're going to be learning about each one of these symbols, when they're appropriate, when they're not. And we're going to be kind of adding it on as a layer to the dimensioning that you're doing right now, which is considered rectangular dimensioning. So GD&T is going to be like adding these symbols and understanding and knowing what they all mean. GD&T is part of the dimensioning standard. So it's not like we just do rectangular and then we just add GD&T. It almost feels that way because we have a class dedicated to it, but it's a standard that both of them are really used at the same time. So we kind of added on a little bit later because it is a little bit more complex and there's a couple more rules and it's not as intuitive. So, but it is considered part of the dimensioning standard. So we always are considering those when we're designing. So that will come later on, something to look forward to. So this brings me to the end of our PowerPoint presentation here. What I want to do before I put you on a break is I want to look at the homework assignment associated with this. So in the classroom, I have the handouts, but if we go back to Module 6, you will notice that there is an assignment for tolerances, okay? So if we click on this assignment, here is, for those who aren't here physically in class, you'll notice that we have the Module 6 assignment PDF, and I'm going to be handing that out in class here. So if you want to click on that and open it up, that would be great. I'm going to get these handed out, and then we will look at it underneath the camera here. Okay. Okay, so as we look at this assignment, the first sheet is just a cover sheet giving some information, and it just says review the first couple pages on LMC and MMC. So let's look at what we have here. So you'll notice here that we have this MMC and LMC, and on here it talks about it, you know, it's in referring to the examples that we see down here below. All it is offering, and it's labeling dependent on if something is an external feature or an internal feature, what its maximum material condition is and what its least material condition is. Okay, so this is going to be terminology we're going to start using more and more throughout the program. So so you'll notice here that we have a pin or a shaft. Those are considered external features. And the reason it's an external feature, I like to think about it, since you guys know about micrometers, calipers, it means that when I want to find the size of that feature, I'm going to collapse down on the outside of that part to get it, or it's on the external part. Okay. So here, my MMC size is going to be the maximum size. Maximum material condition is going to be the largest size of an external feature. Now, an external feature doesn't have to be round. It can be, I'm touching the sides of my table here. This is an external feature. If I want to know what the length of my table is, I touch the outsides. If I want to know what the width is, that's another external feature. A thickness, anytime, and so it doesn't have to be a round. We see it a lot of times as round features, but it doesn't have to be. Least material condition is going to be then the smallest size, the opposite side there, you know, of the limit. When I look at an internal feature is when I take material away to create it. So a hole is the natural internal feature to the external, that's a pin. All right. But it can also be a keyway. It can also be a key seat. It can be a slot. So anything that I'm taking material away to create it is an internal feature. And I say, I have to go in and I have to expand out to actually touch the sides of it to get its side. So if I have a calipers, for instance, I'm going to kind of go in, I'm going to collapse in, but then I'm going to expand on the inside of it to get what that size would be, like on a hole or a slot or whatever it would be. Okay. And so in this case, notice the difference. The MMC size is the smallest size on an internal feature. It's the largest size on an external feature. It's the smallest size on an internal feature. Okay. And then the LMC is the largest size on an internal feature. So the 24.2 is my LMC. The 23.8 is my MMC. Okay. So the externals, I think, go along with the normal. So the maximum material condition is its largest size. The least material condition is its smallest size. And then if you're trying to learn it, the internal features are just opposite. Okay. So my MMC for a hole is going to be the smallest size, and my LMC for a hole is going to be the largest size. Okay. The other way you can think of it is after that feature is made, the maximum material that's left behind. So when you look at an internal feature, the smallest hole is going to leave the most material behind in whatever it was put in. I don't know if that's a way to think of it, but that is a difference. So it's important to understand that. Okay. And then there's a review here of allowances. Okay. When we have a positive allowance, that's where we have a clearance. And you'll notice that our pin is smaller in all cases than the hole that it's going into. Over on the right-hand side, we have a shaft that has a negative allowance. So in this case, that means that we're going to have material that's competing for the same space. And we're going to have a press fit, an interference fit. Okay. So down here, they use the limits of the shaft and the limits of the hole, limits of the shaft, limits of the hole to calculate either one of those. And we'll notice that when we take the MMC of our hole, smallest hole, minus the MMC of the pin or the shaft, largest shaft, in the first case here on the left-hand side, we have a positive 1,000. That means that there is a gap. There is clearance there. And when I put these together, no problem. They're going to go together freely. Over on the right-hand side, on the other hand, same hole. So the MMC is 0.999, smallest hole, minus the MMC of the shaft, largest shaft. In this case, it's 1.004, adding 1,000th of an inch to that nominal size. And now I get a negative because I'm always taking the hole minus the shaft. Negative means now I've got interference. I've got, some resistance when I go together. Okay. That doesn't mean that that's bad. That can be by design, but that's gonna shake out here as a positive or a negative. So positive is always clearance. Negative is always going to be an interference. So now what you get to do on the following sheet, it's not a quiz. It's just called that on this piece of paper on this handout. It's something that I used in the past, and I still continue to use it. I thought it was a good practice for you. So you'll notice here that you have pin C, hole D, pin E, and hole F. And above you have the sizes with their appropriate tolerances. Now what you're going to do is you're going to identify and answer each one of these questions. So the first question here is, what is the MMC of hole D? Now remember, if you need to look back, the MMC size for an internal feature is the smallest size. So when we're looking at a hole, the MMC is going to be the smallest size hole. So if we go down here, since it's hole D, which is right here, the smallest size based on the dimension that you see there is what you're going to put in number 1. The MMC for shaft C is going to be its largest size. So here too, you're going to be looking at, okay, taking that nominal number, adding this time the 5,000ths, and that's going to be your answer for number 2. Okay. And then it's going to ask about allowance, positive or negative. Is that clearance or interference? The example for calculating the allowance is on the very page before this. So reference that. You're going to use those MMC sizes to determine that. And yeah, Okay, so you're going to get 2 opportunities, one for the left-hand side, pin and hole, and one for the right-hand side, pin and hole. Any questions on that? Right? Then as you move forward, then I just have, this is just kind of, I'm throwing these in here. I'm like, this is kind of a good time. It's kind of it's not a huge assignment, but this is called, we're looking at a couple supplemental drawings. So on the following page is this part number. And I want you to answer the following questions. You just simply fill in these values. What is the part name? What is the drawing size? What are the units of measure? Blah, 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 blah. Okay. And you're going to go down and you're going to reference this print right here. Okay. That print right there. And then you're going to do a similar thing, a little bit different questions for the last page here. All right. So a little assignment relative to tolerances. Okay. So that is going to be, I have that due tomorrow, the end of this week. Nice, tiny little fun assignment. Okay. So with that, what we'll do is we still have fasteners to go over in this module. So I'm going to give you guys a 15-minute break, and then we'll come back and we'll look at our next subject.